Housekeeping. Remember, a week on Friday you have your presentations. They will be very strictly to 4 minutes. I will time, and at the end of the 4 minutes you just stop. That's it. Even if you're not finished, you just stop. That's it. Sorry, but it's the only way we'll get through everyone, because everyone's got very tight schedules. You have an assignment. The assignment is not due on the Friday of week 11, it's now due on the Friday of week 12. It has only 2 questions, so it's a nice easy one. I have put up, if you haven't already seen it on the web page, the exam for last year that was set by Gary Glonick, and a set of solutions for you to give you an idea. The main difference between his exam and my exam is that I have had more of a focus on interpretation of our output and our coding. So there will be some extra questions on interpretation and using our output and obviously our coding. So, don't just sort of think it will be identical to Gary's. It will be very similar. The other thing to always do is go through assignments. I try and make sure the assignments. Obviously, you won't have seen everything you get in the exams. It should be a warning to all of you that are not doing an honors exam. We assume that you are not just turning up, but you're thinking about this course, you're reading around this course, etc. So if at any point I've said, that's an interesting thing, put that as I better check I can do that between now and the exam. It's always worthwhile. The main textbook I have been going through is the James et al. And I've given you a copy. Flick through it, see if there's any extra bits in there. No longer is it this idea that if it's not in the lectures, it can't be tested. This is honours, not undergraduate. We will push you a bit more. And I'm saying that not just for me, but for other courses as well. The classic one I was mentioning this morning to one of my students is I had an honours student complain because at one point in the exam, someone had said, you may assume it's a uniform 01, and they said, but it wasn't in the subject. You were all at the end of an undergraduate degree in statistics. You should know a uniform 01, etc. So just make sure you have these things covered.
This is an obstacle course.
Yeah, there's an obstacle course, and I may have been lying to Anthony because he asked me why is the exam so early in the exam period, and I said, well, by the time you take into account all the sections of the exam and how long it is, we have to give you a break every 4 hours, you might not get it finished within the exam period. I may have also mentioned there was an obstacle course.
That would be a lot more fun. Yeah, I'd be down for that.
What?
I'd be down for an obstacle course.
An obstacle course? A statistical obstacle course?
Can we have the option to do either like a written exam or an obstacle course?
Yeah, but it'd basically just be Gary with a sniper rifle. I always wanted to get you lot. And let's face it, Gary is going to be because he looks like, doesn't he look like retired action man? You'd say, well, look at that, and go, that is, see, it is, isn't it?
Still recording.
I don't care. He sacked me 4 weeks ago. The fact that I just turned up is he doesn't know we're in this room. Cool, let's do MDS then. So, multi-dimensional scaling. So, we have at least one expert in the room, so when I get it wrong, you're not allowed to laugh and point. So, we're still in this unsupervised learning, and we had the idea before of, PCA. But imagine you have data where you don't actually have the points in space. All I give you are the dissimilarities. If I just gave you the dissimilarities, I just gave you the distances between points, what do we do then? And what scaling methods will do is they will give us a possible coordinate system of points. So imagine I just come along and go, I'm not going to give you the gene sequences, I'm only going to give you the distances between 2 genomes. How would you now sort of represent that in a coordinate system? So there's 2 main types. There's classical scaling, where the dissimilarities are Euclidean distances, and then there's ordinal, where we only use the order of the dissimilarity measures. When I say Euclidean distance, often there's more distances like that, but they're all nicely behaved. I'm not going to do ordinal scaling in this one. I'm just going to focus on the classical scaling. So, notice I keep using the word dissimilarity or dissimilarity coefficient. I'm trying to avoid using the word distance. So I'm going to define a dissimilarity coefficient. So we've mentioned this a couple of times, but let's just recap it correctly. So we're going to have 2 points, S and R. And we're going to have these constraints to call it dissimilarity coefficient. First of all, the dissimilarity coefficient for the point S and R will always be greater than or equal to 0 for every R and S. Next thing is, the dissimilarity coefficient of R with R will equal 0 for every R. And then we've also got that the dissimilarity coefficient from R to S is the same as S to R, or we have symmetry. So you're basically saying it's always non-negative. If it's 0, it's the distance to a point. And I'm now using the word distance, I should be very careful. And it's got symmetry. If I actually add in an extra one, which is the dissimilarity coefficient from R to T plus the dissimilarity from T to S, is always greater than or equal to dissimilarity from R to S, or what we know as the triangle inequality. If I have all four, we have a thing we call a metric, and it's what we often think about as a distance. You'll find that people do use these, people use the word distance a lot. And you just have to really read very carefully when you see that and say, when you say distance, what are you actually meaning? Is it a metric or is it a dissimilarity coefficient? So here's some standard ones. You've got the Euclidean, where basically you've got two vectors and you work out the squared distance between each coefficient in that vector, square it, add it all up, which is your standard Euclidean distance. You've got your Manhatten, which is where you look at the absolute difference between. It's also called the city block distance. And you'll see when we get to an example of why it's called the Manhatten. Basically, you can't go as the crow flies, you have to go along the blocks, across and up, etc. And then the Minkowski, which is where you take your absolute value, you raise it to the rth power, you add them all up, and then you take the rth root. And if you look at that carefully, you'll notice that really the Manhatten is a Minkowski when r equals 1, and your Euclidean is a Minkowski when r equals 2.
Are these not actually metrics?
These are metrics. Okay. Yeah. So you can say they're actually all the way up to metrics, but by being a metric, they're at least a dissimilarity coefficient. Yes, they'd all be metrics. So here's my simple example. I have 4 points. So, and these 4 points, we can start looking at the various distances between them. So, hopefully. First of all, remember we have this function called dist. So if I take my data frame and do dist, you can see that this is doing what I expect. If you look at difference between, the 2 points on the left-hand side, that's the length of 2. In fact, anything that is vertically or horizontally has a distance of 2. The only time you don't get that is when you go across the diagonal where you have what hopefully is the square root of 8. When you get the Manhatten, now you get something different. To get from, for example, the bottom left to the top right, you can either go across and up or up and across. But basically you have a total distance of 4. And you can also, your distance has Minkowski built in as well. There's also things like the camera in there as well. You can go and have a look at the dist function and see the different methods that you have.
Why didn't you choose b equals 3?
Yeah, it was just do it.
No.
There was no particular reason. What about binary data? Well, they also have similarity measures. Often what they do is they will set up an incidence matrix where they might, for example, in this case, we have 5 different species and we've given a 0, 1 for a particular attribute. So do they have a tail? Do they live in the wild? Do they have a long neck? Do they live on farms? Are they a predator? The farm animal, I mean the human lives on a farm, so is it a farm animal? Is it a predator? Does it have 4 legs? So you can take this and then you say, well, what's the distance between any two individual animals? So they do a thing called an association table, where you're just saying, first of all, where do they have the attribute, both of them, or how many do they have attributes in common? How many do they not have the attributes in common, and then how many where one, in our case, animal has the attribute and the other one doesn't. So for example, if we go back to the lion and the giraffe, we can see they have 1, 2, 3 attributes in common. One where they both don't have the attribute at the same time, and then you've got this one, the long neck, which the giraffe has and the lion doesn't, and this one, predator. The lion is a predator, the giraffe is not a predator. That's a lie. The giraffe is actually a well-known predator, but they keep it quiet so they get tourists in Africa. It's one of the largest and most scariest carnivores known. It's actually up there with the hippo for deaths.
Interesting variable. Do you have like a short neck option as well? Like, you know, right no neck. Is that like a variable?
Well, it's long neck or not long neck.
Yeah, well, what's a long neck? Yeah.
Well, it's what a giraffe has. Whatever a giraffe has.
It's a giraffe or more.
Yeah, it's a giraffe or more. Which of those that's not the giraffe did you look at and go, that's got a long neck?
Well, I just looked at the long neck variable and thought, why don't you call it giraffe?
Yeah, but there's quite, well, actually, there's no others that are quite as specific as that.
Does the swan have a long neck?
Yes, yes, but the swan's not on this list. Yeah, swan's definitely got a long neck. It's just, emu would be there on the long neck. Ostrich would be long neck. It's just not on my list.
Have you operated on the giraffe before?
No.
Did it try to make you?
No, I've done stuff with ostriches, so I have done the long-necked animal surgery type thing, but giraffe is not one that I've done. So how can we take this standard association table and convert it into measures? Well, the first one is the simple matching coefficient, which says what proportion of those things do they match one another, so they both have ones, both have zeros. Now that's not a dissimilarity measure, that's a similarity measure, so you do 1 minus that. The same with the Jacquard's coefficient, that's a similarity measure. The Hamming distance is where they disagree. So the B plus the C is the ones where they disagree. And you can have a look at, just if you want to check those numbers, here's where I have my similarity matrix. I would see, for example, that the giraffe and lion are quite similar according to our attribute measures. You see the cow and sheep are quite similar, but your cow and your human are quite far apart. And the worst is your giraffe and your human, mainly because of this long neck thing. Hamming. So this is now our distances. So you can see the human and the giraffe have a Hamming distance of 5. And finally our Jacquards. So you've got these measures, etc. So if we had something like that, if I gave you that type structure, could you somehow put these things on R2? Could you have some sort of coordinate system? So that's what we're going to look at. So what I'm going to do is I'm going to go with the easy forward problem to set up the notation, etc., and then say, well, let's go backwards. So let's start with the fact that we have our points. So we've got our matrix X for n points in p-dimensional space. And we can create a new matrix called B, which is n by n, where we go X, X transpose. And there's how you would calculate. And we're going to denote the Rth term of B by BRS, and you can see it's just basically the inner product of those things. Okay. So as always, here's our example of the points we saw before. So if I calculate B, I would go X times transpose X, and there's my n by n matrix. So I had altogether then 4 points. So the nice thing is, you can actually get your squared Euclidean distance directly from B. So if I'm going to denote the squared Euclidean distance between point R and S, it's going to be dRs squared, and I'm going to create a matrix, an n by n matrix, of the squared Euclidean distances. And I can calculate that by just taking my B and going, get me the BRR element plus the BSS element minus the 2 BRS, and that gives me the values. So I can get my distances, my squared Euclidean distances, directly from that B. Oh, that's a nice idea. I should write that down. That is a good one, actually.
But it's already been set.
Well, only the first 2 days has been set. We've got a lot of freedom on that Friday. I mean, obviously, Ashley's already challenged us all to a bit of a drinking competition. She said the drinking of beer, bit of my specialist subject, to be honest, at that point. A mixture of port and Guinness is going to be a hard session. You wish you're back in that exam.
I'm choosing obstacle course instead of Guinness.
That's so
We did
sad.
that before the obstacle course, right?
No, we do it while doing the obstacle course.
You showed that Scully and Guinness
Yeah,
running
just
on
climb it. Hey! We used to do 3-legged pub crawls. They were great fun. Anyway, so here's me just showing that it works. So there's my little bit of code that takes my little example B matrix and calculates the D matrix from it by using exactly that calculation. And then just to make sure that at least passes the stupidity test, I just use my distance matrix to get the Euclidean, and then I just square it. And it seems to work on this 4x4. Obviously on bigger matrices, we'll wait to see in the exam whether it actually works or not. So, what about we're going the other way? What about I come along and go, here's my dissimilarity matrix, here's my D. Can you now give me the coordinates? Well, first of all, it's an unconstrained problem. So we're going to add an extra constraint. We're basically going to say, we're going to set what they call the center of gravity of these points at the origin. So basically, if you add over all the points for each individual coefficient, they will add up to 0. Just gives an extra constraint. And that extra piece of information will mean that the row sums and the column sums of B are 0. Okay? God, if I have all this in, it's going to be a long exam, isn't it? But anyway, never mind. It's not my time. So, you can basically take our setup and you say, fine, I'm going to take my D matrix and I'm going to sum over R, or so I'm going down the columns, or I can add over the rows, or I can add over the whole thing. And what you find if you do that with that extra constraint, you'll find that the summation as R goes from 1 to n of my squared distances from R to S. So in this case, this is adding along each row, is equal to this thing T plus NBSS. And T, as you see there, is basically the trace of your B matrix. So it's the sum on the diagonal. If you now do the same thing, but now you add down the columns, you get NB or R plus T, and then finally, if you sum over the whole thing, you'll get 2NT. So you've got a load of equations, you can take them, you can rearrange it, and finally what you should do, if you do that, is you get this nice little equation. If I give you the distance matrix, if you want the RS element of your B matrix, you will take the value, the element, on the R squared element of your D, you'll minus off your column sums, so your row sums, then you minus off your column sums, and then you add the overall sum. In fact, I have not used sums there. That dr dot squared is the row mean. So I've used the shortcut row mean for that. So remember the dot tells you what you're going to actually index over.
Oh, so it's not row sum, it's row mean.
Yeah. So we can take our D and we can get our B. Here's an example. So there's my B that I've created. Set my B is 0, so I've got my D's. And so I go Dij minus the mean of Di minus the mean of Dj plus the mean of D. So I'm taking the ij element of my dissimilarity matrix. I take off the row mean, I take off the column mean, I add back the mean, and then times that by minus 0.5. And that spits out my B. In fact, you don't need to do that. You can actually just do it all in one go. So what you can do is you can just go take D and normalize it by taking off the row means, normalize it now by taking off the column means. Automatically you've made the mean equal to 0 and that just spits it out in one go. So you just basically what they call a double scale. Okay, so we've got a way of getting from D to B. So how are we going to get X from B? Well, there's a couple of ways you do it, but we're going to use an eigenvalue analysis. So, we take B. First of all, note that if the rank of B is K, there will be K non-zero eigenvalues by definition. And we're going to let EI be the unit eigenvector, so we've scaled its length to 1, associated with the eigenvalue lambda I. And all I do is I calculate the square root of my lambda I multiply that scalar by the vector EI, and I call that Fi, and then I just stack them up as each row. So the first one I calculate will be my first row, etc., and that's it. I'm not going to prove it, because you have so much time in that exam, you may as well finish it off. But you'll find that this is a possible X such that X transpose equal B. It's not the only X, but it's a possible, it's a quick, easy thing to do.
So is it F are the rows or columns?
F are the columns. So that's it really. You take your D. From your D, you get your B. You do eigenvalue. You grab the eigenvectors that are not associated with the 0 eigenvalue, and that are your coordinates. And obviously, if you're lucky, you end up with only 2 non-zero eigenvalues. So now you can represent this in 2-dimensional space. So here's my B that we calculated. I use the eigenfunction in R to get it. And you see here, you've got the first 2 columns are the non-zero eigenvalues. And the last 2, that 2.2 times 10 to the minus 15 is basically the equivalent of 0. So those 2 first columns there are our coordinate space. So you'll have a point at 0, 0.7, another point at minus 0.70, third point is at 0.70, and the final point is at 0 minus 0.7. So then all I've done here is I've adjusted that by taking them and times them by the square root to get our final points. So there's our F1. So our first point is actually now at 0, 1.4. The second point is minus 1.40, 1.40, 0, minus 1.4, which looks like this. So this is your coordinate representation. So we started with them pointing them in that nice square. We took them all the way to the distances, and when we came back, you've got a nice square. But it's rotated. You're not guaranteed that if you take coordinates and move them around, get to distances and then come back, they're going to look the same. You might have to rotate them around. It's not bad. Not bad at all. So let's look at another example. Let's look at the UK. So I've got this data set called gv.xlsx, and basically it's got 1,000 towns-cities in the UK, and it gives me the distances between them in miles. Actually, one sheet is miles, one sheet is kilometers, so I did miles because it's the first sheet. So for example, you can see that between Aberdeen and Abbey Wood, it's 520 miles. So we've got this, I've only shown you the first 5. First of all, we're going to have to do a bit of cleaning. You see the first column gives us the name, and I want a distance matrix, or dissimilarity matrix, distance to this one. NAs I want to set to 0. So let's do a bit of cleaning. So get rid of the first column, I set the diagonal to 0, and so here we have our clean data set. So imagine if I gave you these distances and said, convert this to coordinates. So we're going to do our multi-dimensional scaling. So the function to do it in R is really good. It's just called CMD scale. It's built in, UK. That will return me, in this case, 2 vectors for each coordinate. So I grabbed the coordinates, I grabbed the names, and I plotted them. And there's my pictures. So what's that showing you?
A rotated version of where the cities are in the UK.
Yeah, it's not that bad. It's not quite perfect yet. It's hard to recognize, so I'm going to rotate it, I'm going to flip it, and I'm going to put a couple of cities on so we can see.
It's pretty good.
And that's it. Which is quite cool. We just took the distances, we put in the system, and it sort of passed the stupidity test. It's recreated a little bit of UK. You've got Dover, you've got London. Exeter, the bit that sticks out, which is Cornwall's a bit crazy. The stuff up at the top, I believe, up to the left of Edinburgh, is all your sort of Scottish islands, etc.
Clustered a bit more together.
Yeah, didn't work perfectly, but it's not that bad.
They've got really large distances to a lot of
Yeah.
to Western.
And remember, this might be distances not as the crow flies, but how far it is on the road between these things.
Yeah, but it is because it's not symmetric. I was like, well, like, the distances aren't symmetric.
No, there should be. I thought there was symmetric in this one.
Go back to the menu.
No.
Abbey Wood to
Abbots Langley.
Which one?
Abbey Wood to Abbots Langley.
Oh yeah. So it might be on the roads, and one journey takes slightly longer than the other. One-way system, stuff like that. It's okay. It's not bad. So now we're going to look at slightly something different, where we've got a slightly weirder distance. So we're going to look at some grocery data. So this grocery data is it's an incidence matrix. Each row is someone's shopping basket in the US, I believe. And altogether we have 9,835 transactions. And then what we got is it's basically all zeros, and there'll be a 1 if in your shopping basket you bought whatever that column item corresponds to. So for example here, this first one I've grabbed and said which ones do you have. So the first person in their basket, they had citrus fruit, semi-finished bread. No idea. I assume it's one of these ones that's like already just put in the oven and finish it off. Margarine and ready soups. So we've got this instance. Now each transaction is the equivalent of our animal, and each column is the equivalent of an attribute. So we know there's various dissimilarity measures we could use. The one we're going to use is, first of all, I've given you the first 200 transactions. So basically a dot means that they bought that. So here is the first 200 transactions of stuff that people have bought. We sort of want to know, the thing I had to look at was Zweiback.
What is it?
You have to look at it.
2 people have bought it.
It's a type of sort of, I think, like sweetbread almost.
There's a lot of.
A German sweetbread.
I'm impressed by the amount of soft cheese there is.
Yes.
Look at that.
It's this thing.
The speciality flat, the speciality chocolate, the speciality cheese, and speciality bar. So the first thing we're going to do is we're going to calculate dissimilarity, and the one I've decided to use is the Jacquard. you can see that what it's done here is he's taken the Jacquard and actually made it into a dissimilarity. Well, our Jacquard we showed was a similarity. So just do 1 minus. So looking at this, meat and liver loaf have a maximum distance of 1, etc. So now we can just do our CMD scale, and then we will have a look at it. What I've done here is I've just done, the colour is just, I did a quick k-means on the points in space to see if there's some sort of clustering. So I just did a quick k-means. And then you do what I do, which is you spend a long time just going, oh wow. So I think over that, the purple ones seem to be someone who's reasonably quite healthy. They've got vegetables, whole milk, yogurt, tropical fruit and eggs. So let's assume Jono's not in that quadrant, and let's start moving towards the more Jono. There's sort of brandy, liquor, or maybe this one might be quite good. I've got the newspaper. So I heard that Bob Hawke, before he died, about a week before, Tom Pant around his house, and he was basically drinking strawberry milkshake, smoking a cigar, and doing the cryptic crossword.
Sounds good, doesn't it?
It sounds brilliant. That is pretty
way to go.
That's just fantastic. Someone who loves the cryptic. But the idea is that we've taken the transposer, we've looked at it, you're now saying that these points are similar in space, they're close together in space, because they appear together a lot. I mean, this simple analysis is what they do when they'll say things like, you bought this on Amazon, people like you also bought this, this, and this. It's how recommender systems work. It's called market basket analysis. And you see some weird stuff that actually sort of doesn't make sense, but it's still there. There's a lot of alcohol together.
A lot of meat and dairy up at the top there.
Yeah, I did zoom in a little bit on that thing. Because the point where you go into somewhere and you go, I want nuts, prunes, liquor as an appetizer, not your standard liquor, which is your main meal, and dental care. To be honest, I think once you've got that life where you've got brandy, nuts, liquor, I don't know what finished products are as opposed to, I don't think you need dental care. I think dental care is the thing that's in the past.
You've accepted life at that point.
What I liked it there, it's basically there's just tea, rum, sauces. Again, my life. It's just, this diagram's my life. Just various bits of my life as you go from student years to slightly not so student years. I had a lot of fun looking at this.
It's
Very
okay, we use artificial sweeteners, so you can cut down the
An abrasive cleaner. It's just
Can we just, why does this data exist?
Specialty fat.
Why?
I understand that these companies want to store the data of who bought what and stuff, but why is it public on R?
It's an old data set, but just so you can play around as an example, so you can play on it. So you can learn market basket analysis. But every time you have flybys, they purely are doing it so they can get this data. You are basically saying, please take my data.
It's okay, you earn points. So it makes
But
it
it's
more
always
difficult.
thing, if you don't pay for it, you are the product. Simple as that. Every time you get on Facebook, thank you very much. Every time you tweet, every time you have a flybys card, every time they say, would you like to be part of our loyalty? What they should say is, hello, we'd like to know everything about you there is so we can use you to sell you more shit. And this is the classic one. Recommender systems, Amazon, all that sort of stuff. Amazon, as soon as you went online, they loved it because we now were willing to give them as much information as possible about what we buy together. And they do, I mean, there's more, there's better systems than this, but this is an early way of, a quick, dirty way of doing market basket analysis. Now, if you want to know more about MDS and more advanced methodologies, that lady there can tell you all about it. So, it is still a useful area of research and a quick way of looking at it. Other uses I've seen a lot.
Why did you choose Jacquard?
I thought I'd try it. It was more of a try. Normally I try different ones and see how they look, but Jacquard was just an...
Did you check the other?
No, I didn't. No. This was more of an example. If I was properly doing this analysis and I was looking for it, I would definitely try all the different dissimilarity measures, have a look at it, see if I'm seeing anything of note. I do a quick, to choose a number of k-means, I did do a quick hierarchical clustering and have a look. But I would try, in this sort of thing, whenever you have multiple ones, I would try all the different dissimilarity measures and check them and do it that way.
Is hierarchical clustering the one where you go like 2 k-means, 3 k-means?
No, that was the one we did last week where we were producing dendrograms.
Oh, right, yeah.
You find with all these methods, which are, as I said, under the unsupervised, there isn't a truth you can compare to. You're not training it, you're just looking for patterns. So the other reason why I only quickly did check odds on this is I tried another 6 data sets before I found one that at least had something interesting. Because I wanted some non-Euclidean type dissimilarity, and I tried lots and lots of different ones, and this is the first one where it sort of made sense. A lot of the other ones just weren't quite as good. But I've seen it used quite a lot. One of the classic ones is, there's a form of MDS that's called principal coordinate analysis, and they use it a lot in metagenomics. So in metagenomics, what you often get is you'll look at different, for example, soil samples, and they will have this abundancy where they will say that when we look at these particular species, you don't have absolute values, you just have relative values. You'll say this species forms 50% of all the species in this sample. So the basic structure there is just a dissimilarity matrix, and then they just do principal coordinate analysis, which when I looked it up is basically an MDS on that abundance type distance. And they use that a lot in metagenomics. So this classic metagenomics is looking at things of, all the different bacteria you have in your bowel, all the different bacteria you have in your hair, your skin, etc. In fact, the classic one is there is more diversity between the bacteria you have in your hair and your bowel than there is between the bacteria that's normally found in deserts and rainforests. So it's the big thing. They now think that metagenomics might be used to look at things like, they think depression might be based on what basically the ecosystem of your bowel is. Weight gain, weight loss, a lot of mental health problems they think might actually behave based on what's in your gut. So it's actually an interesting, it's the big research here at the moment. So if you're interested, go and look at metagenomics, or metaomics as it's called. Cool. That's MDS. On Wednesday, we will do the EM algorithm. Yay, there's nothing better than the EM algorithm.
What's that for?
It's another way of doing unsupervised learning, where we're going to do more of a parametric approach where we say, assume that we have a mixed model of distributions. How can we identify them? But the EM algorithm is a very useful algorithm to know generally, so that's why I shoved it in. I don't want to shove it in because a lot of my PhD was done on the EM algorithm, and I hate it. I hate it with a vengeance. I hate it and its family, and anyone who ever has even gone around their house. So there might be a little bit of anger on Wednesday, as opposed to my normal relaxed Zen self. Cool.
So is it more likely to be the exam because you don't like it, so you want everybody else to not like it?
There is, to be honest, it was all such good stuff we've done in this course. In the end, it was like I didn't want to kill any of my darlings, so I put it all in. It's the first time I've written an exam that comes in volumes. It's brilliant. I don't know why you're worried. My exam won't be the worst exam you do.
Gary.
Yeah. Cool. Any questions? See you all Wednesday. Thank you very much.
Then like I had to cry. Like it wasn't that hard. It was really hard to laugh. Yeah, that's what killed me.